Hello. So the next thing to be discussed today is parametric tests. So on this slide you can see most common parametric tests. Of course, the list is much longer. So this is t-test or two-means test in Gretel, when you analyze whether means in two samples are equal. Analysis of variance or ANOVA, two variances test in Gretel, when you analyze whether variances in two samples are equal. And finally, two proportions test, when you analyze whether two proportions in different samples are equal. We will start with t-test. So here you can see the formula according to which t-statistics is calculated if we assume equal variances and non-paired samples. So this variable stands for the average value of variable in the first sample. This one stands for the average value of variable of interest in the second sample. And what you can see here is the variance in the sample. So if we assume that variances are equal and samples are non-paired, then it's just equal to the sum of variances in two samples. So we will perform this test in Gretel. You can find the Excel spreadsheet which is used for analysis in materials for this lecture. This is for test 1. So we would like to compare whether GDP per capita in Poland is different from GDP per capita in Belgium. Please pay attention to the fact that this dataset is structured in a different way than the panel dataset you would use for regression analysis. We analyze only one variable. So this one stands for GDP per capita in Belgium for this period, because of course we need several observations at least. And this one stands for GDP per capita in Poland. So what I mean is that when you analyze two variables in Gretel, they should be in separate columns. Otherwise, Gretel will have some troubles with interpreting the data. So I already, just give me a second because I want to perform this test with you. So I already uploaded the first dataset to Gretel. Now I click Tools, Test Statistics Calculator. I choose two means. So first we put GDP for Belgium. Second, we put GDP for Poland. We assume that two populations have the same variance, and we would like to analyze the graph of sampling distribution. Okay. So this is the output, the graph, and the output of the test. It's also presented on the next slide. So this is t-distribution for our number of degrees of freedom, 22, and this is our test statistics. So null hypothesis of this test states that difference between two means is equal to 0. If we put Belgium first, then this difference is calculated mean of GDP per capita in Belgium minus mean of GDP per capita in Poland. This is the statistics for this test. So two-tailed p-value is very small. It's less than 0.01. You can easily check this. So in order to know the exact value of p-statistics in more convenient format, what you have to do is to put this to Excel. In my case, I have to replace dot with the comma, and I have to change format of the cell. So instead of scientific format, I want to have number. As you can see, this number is ridiculously small, so here it is. As you can see, it's definitely smaller than 0.01. That's why we can safely reject zero hypothesis of the test. The same applies to one-tailed test. Again, In order to know whether this is right-tailed or left-tailed test, you need to see this distribution. So first we put mean of Belgium, then we put mean of Poland. So that's how difference in means is calculated. And you see that the respective statistics is positive. So this means that mean of GDP per capita in Belgium is higher than mean of GDP per capita in Poland. So that's how you interpret the result of the one-tailed test. If we put Poland first, then difference in means is calculated as mean for Poland minus mean for Belgium. In our case, the statistics is negative, which indicates that mean of Poland is smaller than mean for Belgium. And based on this, we can conclude that mean of GDP per capita in Poland is statistically significant. I wanted to say statistically significantly lower, but it sounds ridiculous. Okay, so you can conclude that this difference is statistically significant and smaller than 0. So just to conclude, the sequence in which you put variables to the test, like first GDP for Belgium or GDP for Poland first, will actually affect the way in which you interpret difference in means and the statistics. But basically both results are identical. So in the first case you can say that mean in Belgium is higher than mean in Poland, and this difference is statistically significant. And in the second case, mean in Poland is lower than mean in Belgium, and this difference is statistically significant. So basically, those two statements are just identical. Okay, so in our another example, we would like to compare whether GDP per capita in 2019 is different from GDP per capita in 2020. For European Union countries. So this is test 2 spreadsheet, and here I have uploaded it to Gretel. So we use tools, test statistic calculator, two means. Again, now we compare GDP in 2019 to GDP in 2020. If you wonder why we would like to do this, is because of coronavirus. So maybe we want to check whether GDP per capita in European countries is lower in the first year of the global pandemic. Okay, so here we are. Again, this is our distribution. As you can see, the difference is not that dramatic. So even though GDP per capita in 2019 is lower than GDP per capita in 2020, because in our case we subtract mean for 2020 from the mean in 2019. This difference is not statistically significant. So for two-tailed test, it's more than 0.9, and for one-tailed test, in our case left-tailed test, it's close to 0.5. So we definitely cannot reject zero hypothesis. And we have to conclude that there is no statistically significant difference between GDP per capita in 2019 and GDP per capita in 2020 in European Union countries. So t-test is based on t-distribution, and ANOVA, like the next test we're going to discuss, is based on f-distribution. So on this slide you can see a typical F distribution for D1 and D2 equal to 4 and 10 respectively, and this is the formula. Yeah, looks very complicated. So when you perform ANOVA test, by the way, this is the formula for calculating F statistics in ANOVA test. The interpretation is as usual. You do not compare two means, but instead you compare two variants in two different groups. Sorry, that should be ratio. So actually ANOVA calculates the ratio of the variance between groups and the variance within groups, and larger value of this ratio implies greater dissimilarity between the groups. So we will perform ANOVA test using the same data as we did for t-test. So we want to compare GDP per capita in Poland and GDP per capita in Belgium using ANOVA. So you have to upload this file again, test1, tools, test statistics, and now you have to choose two variances. So we pick Belgium, we pick Poland, and zero hypothesis says that ratio of variances is equal to 1. Under this condition, those two samples will be concluded to be equal. Okay, so on this graph you can see not T distribution but F distribution, very similar to the slide we discussed before, and this is test statistics. So you can definitely see that two-tailed p-value is less than 0.01 and one-tailed p-value is also less than 0.01. In other words, we can safely reject null hypothesis that population variances are equal. Based on results of two-tailed test, we can say that they are not equal, and based on the results of one-tailed test, we can see that GDP per capita in Belgium is greater than GDP per capita in Poland, because please remember that here we start with Belgium. So interpretation is very similar to interpretation of t-test we discussed before. Another example, so now we want to compare GDP in 2019 and GDP in 2020, but this time we will use ANOVA. Unfortunately, we have to upload this spreadsheet again. So tools, test statistics, two variances, GDP, okay, so this time let's start with 2020 and then 2019. Okay, so this is the output. Just give me a second. I will just remove all the redundant files. Okay, so here we are, and according to the results of ANOVA, even though GDP per capita in 2020 is slightly higher than in 2019, because this time we used GDP in 2020 as the reference. The results of two-tailed test says that variances are equal. We cannot reject null hypothesis, and the same can be concluded based on the results of one-tailed test. In our case, of course, it's right-tailed test. So even though GDP in 2020 is higher than in 2019, this difference is not statistically significant. So in both cases, we just failed to reject null hypothesis. So what I wanted to mention is that you can see that ANOVA and t-test usually produce very similar results. However, ANOVA is considered to be more sophisticated, so I would say it's up to you. And finally, we use two proportions test when we want to compare two proportions in different populations. Consider the following example. There are 50 female students and 60 male students who participate in Introduction to Econometrics class. 5 female students and 12 male students failed the final exam. And based on this, we have to say which gender is better in econometrics. So proportion of females who failed the test is 5 divided by the number of females, 0.1. Proportion of males who failed the test is 12 over 60, 0.2. So for this, you have comment in Gretel. Again, tools, test statistics calculator, and we use two proportions test. So for females, the proportion is 0.1 and number of females is 50. For males, the proportion is 0.2 and number of males is 60. So zero hypothesis says the difference in proportions is equal to 0. And this is the output of the test. Just let me close all the... yeah. Okay, again, we started with females, so even the position of our statistics indicates that number of females is smaller. However, we do not know whether this difference is statistically significant. So we have to look at the results of the test. And for two-tailed test, we fail to reject zero hypothesis. So we cannot reject the hypothesis that population proportions are equal. However, for one-tailed test, to be more specific, left-tailed test, we can reject this hypothesis at 10% significance level. So we can indeed conclude that proportion of females who failed the test is not bigger or equal to proportion of males who failed the test. We have to reject this hypothesis in favor for the alternative hypothesis, which states that proportion of females who failed the test is lower than proportion of males who failed the test. So this is it. Okay, of course, as I said before, there are other types of parametric tests, for instance, paired parametric tests and so on, but during this course we will not concentrate on this issue that much. So yeah, that was it when it comes to parametric tests. In the next video I'm going to discuss briefly most common non-parametric tests. Hope you enjoyed this one and see you in the next video.